Hello everybody, welcome back. This is lesson 3 on our linear relations journey here. We're going to be looking at domain and range today. So domain and range usually is a tricky topic for students when they first learn it, but after a little bit of practice and they get used to it, they wonder why it was so difficult in the first place. So let's just dive right in and we'll get going. So for domain, we'll start right with that definition. That's going to be the first element that's in a relation. Now, basically, it's the set of all possible values for the independent variable in that relation. So for us, that is going to be typically that's going to be x. Okay, so whatever is our independent relationship, our independent variable of our relationship, well, let's go on our x-axis. Now for range, that's going to be the second element of a relation. So it's going to be the set of all possible values for our dependent variable. Typically, that is y. Okay, so those are going to be the ones on our y-axis, the ones that depend on whatever that input is. Now there's some differences between types of data. So we could have discrete data versus continuous data. Now, if something's discrete, that would mean it only takes on certain values. It can't have values in between. So for example, think about what happens when you roll a die. There's 6 sides on it. You're never going to get 5.5 on that die. It's very rigid as to what numbers it could hit. So rolling a die would give you discrete values from 1 to 6. It only appears as those dots that are on the faces. So, let's say it's only values 1 through 6, right? You're never going to get 1.3, 6.2, nothing like that. It'll only be the whole numbers 1, 2, 3, 4, 5, 6. Okay. Shoe sizes is another one. Really, it's like your whole number sizes and your half sizes. There's no other choice there. So there's not a shoe size of 9.2, right? It's either 9, 9.5, and that's pretty much it. So that would be another example. If it's continuous data, would be data that can take on any value within a range. So height is 1. Oops, I can't write today. Height, weight. Okay, so those ones could be like decimals. You can get as specific as your measuring tools allow you to. Time is another one, right? You can have hours, days, seconds, milliseconds, hundredths of a second, thousandths, 10,000ths of a second. So you can just keep going. And again, you're limited by the precision of the measuring device you're using. Okay, so these would all appear as a line on a graph. I guess I should say the ones up above appear as dots on a graph. Okay, so the specific values would be discrete. If it's continuous, it'll continue on with the line. Okay, there's a bunch of different ways you can express the domain and range. You could use words, number lines, what we call set notation, which is the one people usually struggle with. Interval notation is the easier of the two, and then lists. So we'll see what happens when we look at all of these. So let's take a look at a graph that looks like this one. Okay, and we'll do all 5, just so we can see exactly what's going to look like. So if we're going to use words here, we're really describing the values that are allowed. Now, if I look at this graph, really is a line segment because it ends, right? It's got those 2 endpoints, which you can see in blue, one at 1, 1, the other at 3, 4. So let me just move my mouse here. Okay, that's a little bit better. So you can see those values there. So those are really the endpoints of our line segment. Now that doesn't go on forever, right? It ends at those 2 blue points. If I use words to describe that, we have to talk about both the x direction and the y direction. How far my graph is actually allowed to go from left to right, and same thing in the vertical direction. So from left to right, that's talking about the domain. We're talking about the x values. So for domain, if we describe what happens in a sentence, that's going to be all values between and including, that's important, and including 1 and 4. If I look at this in the x direction, so we're traveling horizontally, I start at 1, right? That's my first value for x, first element in that relation. Okay, since that circle, that endpoint is actually colored in, it's shaded, I have to actually include that endpoint as part of it, which is why we have to say including. And then I'm going to keep going to the right, because that's which way my line segment goes, and it goes all the way to 4. I don't have an x value that's larger than 4. Okay, the line tells me it could be any value in between, so 2.5, somewhere halfway, there is a dot that exists there. Okay, so I have to include 4 as well, so that's domain. For the range, and let me zoom in just a little so I can write the range, that's going to be all values between and including, again, because those endpoints are shaded. But now I have to think about this in the y direction. Okay, so the lowest y value, the first element in that set of y's is 1. Okay, that's the lowest y value. The biggest y value on this graph is 3. Now it doesn't look like there's anything here, but it's all the way over here. So even though the x value is different, the y value is still 3. So this is going to be including 1 and 3. Okay, so there it is in words. 1 to 4 for x, 1 to 3 for y, and that would encompass the entire graph. If it's a number line, we can give this as a visual. So I'm just going to write a D to represent domain. Now if it's a number line, I really am going from 1 to 4. So that could be your max there. There's 1, there's 4. If it's a number line, remember that we shade in everything that's included, and we represent a continuous line to mean that it's going to be everything in between, right? This is how that number line works. Essentially, it's what the graph looks like, but in a one-dimensional picture, right? Only from left to right. Now for the range, it will also show a one-dimensional picture, but you're not going to draw a vertical number line. That's still going to represent, your number line is horizontal. This time it goes from 1 to 3, not 1 to 4. And again, the endpoints included. There's your number line for range. Honestly, the same picture. Numbers are just changed. So there's your number line. Now set notation is what's challenging for students because it's such a new notation and it looks really fancy and it looks more complicated than it is. Okay, so it's a formal mathematical way to give the values domain and range. Typically, it's the most commonly used one in high school math. Okay, usually from math 10, 20, 30, this is going to be the one you're going to see. Math 31, if you're going to use calculus, interval notation actually is a lot better and more common. Okay, so these are going to be the two that are most common depending on the math courses you take. Set notation for sure will come back again. So you're going to see those curly brackets. Those are used to denote a set. That little e there means it's an element of, so we're going to have to specify what set of numbers this belongs to. Integers, whole numbers, usually it's going to be real numbers. And that vertical line means such that. So basically, given a restriction, here's my domain, or here's my range. So we'll start by writing this out. So domain, that's the one we'll do first. So the domain basically is the set of all values of x. Okay, so it's going to be the set of x values given or such that. And then I have to state what that restriction actually is on x. Because right now x cannot be anything. We said it only goes from 1 to 4. So we have to actually state that next. Okay, so the things that x can be, I can start at 1 and I can be less than, x is greater than or equal to 1, which means 1 is less than or equal to x. Right, so this basically says 1 is the smallest value I could be. But we said we could also be 1, so I have to include it by making my equal sign underneath my inequality symbol. Okay, that means x has to be less than or equal to 4. If I write my inequality this way, this says, reading it from the middle, x has to be bigger than or equal to 1, but x should also be less than or equal to 4, which is exactly what this says. It has to be bigger than or equal to 1. My boundary point on the other side is 4, so equal to or less than 4. Now, since that's been specified, we have to say what type of number x is. So x belongs to the set of real numbers. So x is a real number. It could be any decimal, any fraction, any number, as long as it's in between 1 and 4. Okay, that's really what this is saying. So we're going to do the same thing for range. So obviously the range is now not the set of x values, but the set of y values. And it's the set of y values such that 1 is the smallest. Okay, it goes all the way up to y, and then goes all the way up to 3. So this says that y should be in between 1 and 3, and it can be equal to either of those endpoints. Other than that, y could be any other real number. Okay, so you might see that r just as an r, or r with like kind of another line behind it, kind of like the fancy r math symbol. That means the set of real numbers. Either one makes no difference. Okay, so that's set notation. Interval notation basically looks like a coordinate pair, except the type of brackets are going to tell you if you can or cannot include the endpoint. Okay, this doesn't work for discrete data, only for continuous. Okay, so if it's a square bracket, we'll use that if the endpoint is included, a rounded bracket if it's not included, and the infinity symbol if there is no endpoint. So sometimes I could go on forever. Now for our specific example, I have two endpoints of 1 and 4 on the domain side of things, 1 and 3 for the range. So for domain, if it's 1 and 4, we have to decide if we can or we cannot include those endpoints. We said we include them, so that means both of these get square brackets, and that would be your interval for your domain. Okay, for the range, our interval is 1 and 3, and again, we had both those circles shaded in. We had them both being equal to inside of our set notation, so both square brackets again. Okay, but that's interval notation. Very short, very handy, because it tells me it goes from 1 to 4, including both ends. Right, a lot less to look at than set notation. Set notation for sure is the most completed picture. Even tells me what set of numbers it belongs to. Interval notation, just kind of the shorthand tells me a little bit less. Okay, now for the list, you can use this for discrete data when there are minimal numbers to list. I can't really use this for my continuous graph because there's an infinite number of values I could be in between 1 and 4. All the decimals, however many size, right? So I can't really do that for a continuous graph. But if it's for a discrete relation, okay, so discrete date, I should say data, for discrete data, when there are minimal numbers to list. So for this relation given by these 4 coordinate pairs, I could do a list on the domain, and it's going to be, again, we'll use that curly bracket to tell us we have a set of numbers. Remember, we want the domain to be the set of all of the first values, all of the x's, all of the inputs. So the set of values that belongs there is 0, 1, 3, and 5. They're all unique, so I do have to account for all of them. If I do the range, okay, that'll be the set of values that comes second. We only have to state them once. Since there's 2 7s, I don't have to repeat them. So 0, 5, and 7 are our unique values for range. We don't want to repeat. Okay, so we'll even write that. Don't repeat numbers. It's like when we did our mapping diagrams in our last video, we didn't actually repeat things. So I think we talked about, I believe it was territories in the northern parts of Canada. We only wrote them once. We didn't have to repeat them. So if I drew an arrow diagram, I might have multiple domain elements going to the same range element. So if I drew arrows, 3 and 5 would both connect to 7, and that would be part of our mapping diagram. Okay, so let's take a look at a couple examples, and maybe the graphs change, but we can still do all of these to figure out, our domain and our range. So let's at the bottom, right there. Okay. So we will do a few of these. I won't do all of them, so I can give people a chance if you're watching this and you want to try them out on your own. I'll give you the full answer key in the description, so don't worry about that. So we'll do the first couple for sure. Actually, maybe we'll do the first one and one of the discrete ones. I think that's what we'll do. Okay. So for domain, that'll be all the x's again. Remember, we're looking at this in the x direction. So words. Really, the top parts of this graph tell me I have arrows. So if you imagine this is really going to extend in both directions forever, right? It'll keep going to the left, keep going to the right. So really, my domain is going to be all the real numbers. There is not a restriction on what x can be. It's going to continue forever. If I do that for the range, I'm thinking about the y value. So I want to figure out how high this graph goes. And again, the arrows tell me it's going to go up forever. But if I look at this in the downwards direction, it hits a point where it stops. So the smallest y value is actually -1. So as a sentence, that's going to mean all values larger than and including -1. Right? That's really my smallest point. Everything other, all of the other values have to be bigger than that. Okay, if it's a number line then, for the domain, it really does go forever. Right? My number line goes forever because I could have on one side of it negative infinity, and I wrote that like an 8. Okay, so if I think about the x direction going to the left forever, I'm going to get to an infinity, but now there's two kinds of infinity. I could get to the negative infinity side of things, but if I go to the right, I get to positive infinity, where it goes forever. So that's a little tricky for students as well. So there's my number line for domain, but for range, I can see that I have a clearly defined endpoint of -1. Right? That'll be the smallest, because on the vertical side of things keep going up, you're going to get to positive infinity. All those y values up there are positive numbers. So there's your number line. I have to represent basically -1 is included, but I go on forever to the other direction. If I do my number line for this one, basically it would overlap what I had, really show that it goes forever in both directions. Okay, that's going to be our number line there. For set notation, for the domain, since it's going to be all of the values of x, this is really going to say the set of x values such that x is any real number. I don't have to have an inequality here because I could be anything for x. I can just state that it's x is a real number. That's totally acceptable. If I do that for the range, we're talking about the set of y values such that -1 is the smallest and everything should be larger than it. So as long as the value of y chosen is greater than or equal to -1, that can be any other real number. And that completes our set of values. So as long as it fits in that inequality and it's a real number, we're okay. As an interval for the domain, if it's any real number, your interval goes from -infinity to positive infinity. And I can never reach infinity. So both, anytime you see an infinity symbol, it should be a rounded open bracket. If you put a square bracket, that says you can actually reach infinity, which is a logical contradiction, because if you can reach infinity, that means there's nothing larger than it. But if it's infinite, that means it goes forever. So you can't actually reach infinity. If I do that for the range, my endpoint is -1. The other value I need to have is infinity. Now I can definitely reach that -1. I have to include it. It's on my graph. It's shaded in. It's continuous through that point. But infinity, you can never reach. So a rounded bracket. So there's all the possible ways we could do domain and range. I can't really do a list here because it's a continuous set of data. I can't list out every possible value. So there's all of the pieces. Okay, I won't do the one underneath. I'll leave that one. I won't do that one either. And I want to see if people can come up with that one. But if it's a line that goes in both directions, really it goes up forever, down forever, left forever, right forever. A lot of these are going to be infinity cases. Okay, let's talk about maybe something like this. That's very, very different than the one we did. Okay, so I've got now a vertical line, which looks like I've got an open circle on this value, and it's pointing completely straight upwards. So in words, for the domain, again, we're looking for the x values. The only possibility I see here for x is a -1, right? The graph doesn't go sideways at all. So this is going to be restricted to -1. For the range, remember you're talking about the y's. So my y value, the smallest one, is +1, but that really is the smallest, but everything has to be bigger than it. Now I can't include that one this time because that circle is open. So this is all values bigger than 1. Just take that dot out, all values bigger than 1. Now if it's a number line, if we do the domain first, I can't really have a number line because it's at -1. right? That's the only possibility. So technically my number line is just a dot at negative 1. I can't move it anywhere. If it's the range, we can think about having that number line go from one endpoint to the other. But now, my endpoint that has to be there is 1. Okay, that's the y value on our graph that we're looking at. Now that's the smallest y. The biggest y, this graph it actually goes to infinity. So it's going to keep on going all the way up. So there's my number line here. I have to leave that circle open because I don't have any values where y is actually equal to 1. That circle is not shaded, so I should leave it open as well. For set notation, really for the domain, it's the set of all x values given the restriction that x has to be equal to negative 1. That's the only possibility for x, right? I can't have it at 1, can't have it at 2. None of the other ones will work. There's no part of the graph that exists anywhere else other than when x is equal to negative 1. So there's my restriction. Now for the range, as long as it's bigger than 1, we're okay. So it's the set of y values given the restriction. Y is larger than 1, but as long as that is true, it can be any other real number, as long as it's bigger than 1. So if it's a number like 0.5, that would not fit in the range. Okay, it doesn't follow with the elements of this relation. Now as an interval notation, if I only have one value, I can't write an interval. I need 2. Okay, so that one's not available. If I do the range, its interval, that goes from 1 to infinity, but both endpoints should be open here because I can't actually include that endpoint of 1 as part of this interval. Okay, it's not shaded in, so it should be open. So you can see all of them now. So if it's not shaded, I can't say it's equal to 1. My number line can't be shaded. I can't have an equal sign under my inequality, and I can't have a square bracket. Every one of these has a way to account for something not being equal to. Okay, so I can't actually do that here. All of them have to be either open or representing their specific not equal to case. Okay, so there's how we would do that one. What about if it's a bunch of dots? Okay, what happens if it's just a discrete bunch of numbers like this? Okay, so if we do domain, this includes all of the values for x that you could be. So this includes the values. So all of the x values are -2, -1, 1, and 2. So -2, -1, 1, 2. Those are the only possibilities for the domain. Those are the only x values. For the range, this includes the values, values of -1, 1, and 2. So -1, 1, and 2. Even though there's 3 y values of these coordinate pairs that end up being 2s, we only have to include that value once. We really are just talking about the element that's there, not the fact that there are 3 of them. Okay, as a number line, you could do this as well. Okay, so we can throw all those numbers on there. So -2, -1, and I'm going to put 0 for good measure, 1 and 2. Now the only places that we should see dots are on those specific values. I don't have any values in between. I really am just hitting those specific numbers. So 0 doesn't count, I can't connect them, just the specifics. Okay, same thing for range you can do. Switch back to purple. Okay, we'll have our -1, 0, 1, and this is 2. So including those specific values, there should be 3 circles that are shaded in for you. Okay, so those are the only 3 specific values for the range. The set notation, though, actually doesn't really work here because it's not really what you think it is. So I could try having the set of all x values such that, but when I try to, I can't do it as an inequality because I can't be less than or greater than a certain number because I only have specific numbers. So I really should be saying what x is actually equal to. So it's only equal to -2, -1, 1, and 2. It can't be any real number. It has to be these specific numbers. Okay, like it can't be any values. It can only be these ones. -2, -1, 1, and 2. It can't be anything else other than that. So I can't say it's any real number here. For the y's, It's the set of all x values given that y must be equal to -1, 1, and 2. Okay, very, very similar to writing a list, except we don't have the beginning stuff. Okay, I can't do an interval again because I don't have an interval of things. Okay, I have only those specific ones. So as a list, you're going to list out the set of the x values. So -2, -1, 1, and 2. Very similar to set notation. Okay, because this is a set of values. This describes that set of values. The other one, -1, 1, and 2. Okay, so you can do this as well. Now, if you need to really have a difference here, this one is discrete data. Okay, not continuous, no line connecting anything. So we can talk about one last one before we wrap this one up here. So a school is selling tickets to their school play for $10 a ticket. Theater's max capacity is 120 people. Write an equation relating the number of people attending this play to the total revenue. If it's $10 per ticket, however many people come, if you multiply that value by 10, that'll be the total number of money you're getting. So it'll be the revenue that's equal to 10 multiplied by the number of tickets sold, or the number of people attending. So 10 times n. 10 people show up, you made $100. That's what this is saying. So we'll graph this relation. Now we'll come up with labels for stuff. So x, our x-axis is going to be the number of tickets. Okay, number of tickets. That'll be our independent variable, because the thing that changes because of the number sold, that's going to be our dependent. That's going to be revenue. And that's going to be in dollars. Okay, so the amount of money we make depends on the number of tickets we sell. If I do not sell any, I've sold 0 tickets, made $0. So let's do this by 20, 40, 60, 80, 100, 120, and we'll say this one here is 140. Okay, so we'll count by 20s. Now for revenue, might be a good choice to pick some good numbers. So if it's 10 times the number of tickets sold, our first dot should really be at 20, 200. So depending on how you want this scale to go, I think I'm going to count by 200s. Okay, so 2, 400, 600, 800, and 1,000, and then that means the top one should be 1,200. Okay, because 20 times 10 is 200. There's my first data point. And then at 400, I'm going to have another one, 60 for 600, and 80 for 800, and then there's 1,000, and there's 1,200. Now, I could absolutely sell 10 tickets and have 100. So I could have that one partway through. So I should include that as well. So every second spot should also be accounted for. Now, let's see, right equation number of people attending the play, revenue, there's a maximum capacity of 120 people. So I know I can't sell 140. Okay. State our independent, dependent. So independent, state them all off here. Independent, that's going to be our n, right? The number sold. Our dependent is going to be our revenue. Okay, that's in dollars. Oops. Revenue. There we go. Now, this data has to be discrete because we can't sell half a ticket. Okay, I could really sell any number of tickets I want up to 120, but I can't sell half of a ticket. So I can't really, based on the limitations of my graph, put a dot anywhere along that line because I don't really know where those whole numbers are. It's very difficult to tell based on the scale that we have, right? I would have to have my scale going up by ones to really make sure that I can put the dots in the right place. Just based on the scale of the graph, I can't put the dots in such a place. So we'll have to leave it like this, but as long as we have the understanding behind it that I could have, other dots here, then we're okay. Okay, so we'll state the domain and range in words here. So for domain, the school could sell anywhere from 0 tickets to a maximum of 120 tickets. Really, those are my endpoints. I could either sell none and have the show be a total flop, or I sell 120 and I sell them all. Right? Those are really the only two options, and obviously everywhere in between. And for the range, that one's talking about the dependent variable, the money. So the school can make anywhere from $0 to a maximum of 1,200. Right, the number of tickets you've sold multiplied by 10. So if I sell all 120, I've made $1,200 in total. Okay, so there's a little bit of introduction to domain and range. Now the issue is people forget that domain is X, all the independents, and range is Y, all the dependent. Right, that's going to be the struggle. So again, you do have the completed answer key, or you will, by the time this video goes up in that description box. So my advice, please try them if you're using this to kind of supplement your actual teacher's learning, teaching, I should say, your actual learning. Domain and range is a challenge. So for a lot of things in math, practice becomes super important. So if you do need anything, by all means, reach out to me. Send me an email. You can follow me on Twitter, follow me on Instagram, and I can give you anything that you might need. If you ever want to work together on something, if you are a teacher and you found this by chance and you want to collaborate on some project, then by all means reach out. I really look forward to that. But until next time, everybody take care, stay safe, and we'll see you in the next one.